Have you ever just stopped and looked at the screen you're staring at right now and wondered, how? How is this even possible? How do we get from a simple rock, literally silicon from sand, to the incredible technology we use every single day? Well, that's the journey we're going on, and trust me, it is absolutely mind-blowing.
Yeah, it can definitely feel like magic, right? I love this quote. Throw some metal in a box and boom, because that's what it feels like. But here's the secret. Behind all that apparent magic, there's a beautiful and honestly, a surprisingly simple logic. So let's peel back the layers and actually map out this world of computer science, right from the ground up.
So, where do we even begin? Well, it all starts with the most fundamental thing imaginable. We have to figure out how a machine can represent information in the first place. It all comes down to a really simple question. How does a computer count?
It all boils down to this one little thing, the transistor. Inside your computer's processor, there are billions, with a B, of these microscopic switches. All they can do is be on or off. That's it. We represent off with a 0 and on with a 1. That single value, we call that a bit. Now, a single bit isn't all that useful on its own, but what if you group 8 of them together? You get a byte. And with a byte, you suddenly have 256 different combinations of ones and zeros, and that's enough unique patterns to create an entire alphabet.
This whole system of zeros and ones is called binary. It is the native language of every single computer on the planet. And what's so amazing is how this incredibly simple system becomes so powerful. Using a standard code like ASCII, we can assign a unique binary number to every letter, every number, and every symbol. So that A you just typed on your keyboard, to the computer, it's not an A. It's just 01000001.
Okay, so we can store information now. That's great. But right now, all we've built is a very, very fancy digital filing cabinet. How do we get the computer to actually do something with that information? How do we build its brain?
The answer is something called logic gates. This is where things get really clever. By arranging those same simple on or off transistors in specific ways, we can create tiny circuits that make basic decisions. Think of a light bulb with 2 switches. An AND gate is a circuit that decides the light only turns on if switch A and switch B are both on. These simple, tiny rules are the fundamental building blocks for every single calculation a computer will ever make.
Now, at the heart of this whole process, you've got 2 key players, the CPU and the RAM. The CPU is the brain, performing billions of calculations a second. But, as one of our sources so brilliantly puts it, it's a genius with the memory of a demented goldfish. It can't hold on to information. That's where RAM comes in. RAM is the computer's short-term memory. It's scratchpad. It holds all the data and instructions the CPU needs access to right this second.
And these 2 components are locked in this constant dance together, billions of times every second. It's called the machine cycle. The CPU fetches an instruction from RAM, it decodes what that instruction means, it executes the command, and then it stores the result right back in RAM. Fetch, decode, execute, store. Over and over and over, all at lightning speed.
All right, so we have a machine that can process ones and zeros incredibly fast. Fantastic. But how do we, as humans, tell it what to do? How do we communicate our complex ideas to a machine that only understands on and off? Well, at the very lowest level, the CPU understands just one thing, machine code, a pure raw stream of ones and zeros. You see that wall of binary on the screen? All that is just the word hello. Can you imagine trying to write a whole program like that? You would absolutely go insane.
And that is exactly why we invented programming languages. So instead of that unreadable wall of binary, a programmer can simply write this, print hello. This is a high-level language. It's readable, it's understandable for humans, and then special programs called compilers or interpreters do the heavy lifting of translating our human-friendly code into the machine code the computer actually needs.
But what's the logic behind the code? That's an algorithm. The best way to think about it is like a recipe for a meal. Before you write a single line of code, you need a plan, right? A step-by-step set of instructions to solve your problem. When Google Maps finds the fastest route to your destination, that's an algorithm. When your music app sorts a list of songs, that's an algorithm.
And to make those algorithms work efficiently, programmers need the right tools. They use things called data structures, which are just clever ways of organizing information for a specific job. An array is just a simple list. A stack works exactly like a stack of pancakes. The last one you put on is the first one you take off. And a tree organizes data in a hierarchy, just like the files and folders on your computer.
So, let's recap. We've gone from a single on-off switch all the way up to a single program. But how do we get from there to the massive, interconnected digital world we all live in today? How do we scale this whole thing up?
The glue that holds all of this together is the operating system, the OS. This is the master coordinator. It's the software that sits right in between the physical hardware, the CPU, the RAM, your keyboard, and all the applications you want to run. It's managing resources, scheduling tasks, and basically making sure everything plays nicely together.
The sheer scale of modern computing is just staggering. This quote really puts it into perspective. Just think about that for a second. The power we all carry around in our pockets today is almost unbelievable, and it's all built on those simple principles we just talked about.
And of course, when we connect all of these powerful little devices together, we get the internet. And let's be clear, it's not some magical cloud. It's a physical thing. It is a global network of computers connected by massive cables running under the oceans, all agreeing to speak the same language, the Internet Protocol, so they can share information with each other.
So, we've built this incredible global brain. We've taught it how to follow our instructions with perfect precision and at unbelievable speeds. So, what's the next logical step? Where do we go from here?
It's teaching them how to teach themselves. This is machine learning. Instead of writing a step-by-step algorithm to identify, say, a picture of a bee, we just feed a computer model thousands of pictures of bees and let it figure out the patterns on its own. It's a fundamental shift from giving explicit instructions to enabling learning.
And that brings our journey full circle. From a simple on or off switch and a piece of silicon, we have built machines that can process information, communicate globally, and now even learn on their own. We literally taught rocks how to think. The only question left is, what should we ask them next?